So I definitely got cut off on the previous video, so I apologize. So let's go ahead and just start again. A wave has a frequency of 6.53 times 10 to the 5th hertz. Calculate the wavelength of this radiation. Okay, so we're going to go ahead and use the guess method. The given is what is provided for us in the formula or any constants that were given. So it says here that the wave has a frequency of 6.53 times 10 to the 5th hertz. So that's something that's given to us, and I always like to pair it with the variable that's supposed to go with it, the symbol. So F equals 5.3 or 53 or 6.53 times 10 to the 5th hertz. And we're also given C, which is the speed of light. Okay. The unknown, it says that we're going to be looking for the wavelength, calculate the wavelength, so we're looking for lambda. Lambda equals question mark. The equation that we're going to use, remember we have two choices. We could use energy equals Planck's constant times frequency, or we could use speed of light equals wavelength times frequency. And these all should, or sorry, we're going to be using this formula because it's talking about wavelength. So we're going to use the one with wavelength in it. Now we're going to substitute, which means I'm going to take these values up here and I'm going to plug them into the formula down here. So C matches with C, F matches with F, and it looks like this. Now I made lambda really, really big so that we can see it. So we're trying to get wavelength by using algebra to get it all by itself. So what I'd like you to do is make sure you copy this formula or this setup in your notes, and I'd like you to practice solving for lambda. This is just simple algebra, so you're trying to isolate lambda just like you would x. And keep in mind that when you type this into your calculator, you want to be either parenthesis crazy or you want to be using any of the other methods that have been taught to type in powers. Okay, so I have set up a few practice problems, and I do just want to point out a few keywords. And feel free to please pause the video in between each of my little explanations. I will not be providing you with the answers to these right now. They will be provided later. So the wavelength of violet light, okay, right away I read wavelength and I'm thinking I need to be using the wavelength formula. So that is the speed of light equals wavelength times frequency. So I need to be using that first formula. Wavelength of violet light is 380 nanometers. Calculate the frequency of violet light. Oh, recall that nanometers equals 1 meter. Okay, so this is important. When we do calculate this and we spit out a number at the end, your answer is going to be in meters. We need to make sure we put it in nanometers. Okay. Oh, sorry. We actually need to put this in meters. My bad. We need to convert 380 to meters first. Then we can plug it into the formula. So remember that for every meter, there are 10 to the 9th nanometers. Okay, cellular phones typically operate at a frequency of around 850 megahertz. Okay, so it's in mega, so we need to go to hertz. So this is another conversion factor. We've provided you with the conversion down here. And then you need to be able to calculate the wavelength of radiation used for cell phones. Wavelength, which means I need to use which formula. So go ahead and pause the video. I want you to practice setting up the guess method and solving this problem. All right, and then what wavelength of light does 14,000 hertz correspond to? Okay, well, again, we're using wavelength, so we're going to be using the first formula, right? All right, calculate the energy associated with the frequency of 8.5 times 10 to the 8th hertz used by cell phones. This time we're using energy. So we're going to be using the energy formula. That's E equals F times Planck's constant. Okay, so now you guys have done a few practice problems in your notes, and we're almost done. We're going to be talking about the idea of atomic emission spectra. Now, an atomic emission spectra, as you'll learn in the flame test, is something that is unique to each element. It's like a fingerprint for each element. If you look here, we know that a quantum is the amount of energy that's required to move an electron from one energy level to another energy level. So a quantum of energy is actually absorbed, which means the atom takes on energy when an electron increases its energy level. So this electron just moved from here up an energy level, and that takes energy to put more energy or move an electron up to an energy level. So what it means by energy being absorbed is that the energy is put into the atom. Okay, the opposite is true when we take something that's already, or an electron that's in an excited state, and we move it back down to its resting or ground state, this first energy level. That's like the atom relaxing. So it's like releasing its energy, right? So when we move that electron down, we release energy, or we emit energy. So just so you guys know, excited state note, right? Whenever an electron is not in the energy level it's supposed to be, like here, right? It's not in the first energy level, or you can see here, this arrow should actually be down here in the 2p sublevel. That means that the atom is in its excited state. When we're in the ground state, everything is normal, hunky-dory, it looks fine, nothing is out of place. This is the ground state. So here's some summary questions. If an electron were to move from energy level 2 to energy level 4, we are putting energy into the atom because we have to move it up an energy level. So energy is absorbed. It takes energy to increase energy, right? Because we increase from 2 to 4. If an energy or an electron moves from 4 to 3, energy will be emitted because that is when the electron relaxes. So if you were to look at these two transitions, go from energy level 5 to 2 or from 5 to 3, which one would have the most energy? Well, the larger jump in energy level means more energy released or absorbed. Now in this case, because we're going from a higher energy to a lower energy, we're relaxing and releasing or emitting energy. Okay, so I believe that's the end of the PowerPoint. Make sure that you have your whole worksheet filled out, and if you have any questions, feel free to ask your peers or ask your teacher. If your teacher's not here, you can always swing by Miss Lemenz's room after school to ask any questions that you may have.